So when you are doing these, the first thing you need to look at is the index. The index, if you don't see one, is a 2. So now we're going to look for everything that groups in 2s. If it groups in 2s, it can come out. If it does not, it will stay in. I start with the one that is already out there because often people forget it. So that is definitely going to be on the outside. And then I'm going to factor my number. So if I factor this, I'm going to start with a 2 times 36. And then I'm just going to go from there. All right. So then I'm going to look for my pairs. I have a pair of 2s. That's going to come out. I have a pair of 3s that is going to come out. And then I have a 2 that does not have anything with it. It will stay inside my root. For my variables, my x is to the first power. If I use that index rule, that is 0 with a remainder of 1. You can also look at it like I have 1x in the tree. It does not have a partner, so an x is going to stay in. I'm going to look at my y's. I can use my little remainder rule. 3 divided by 2 is 1 with the remainder of 1. Or I can think of the fact that y cubed is y times y times y. And I have one pair that groups and one that does not. So 1y will come out, just like this says here. 1y will stay in, just like my rule there. And then I'm going to look at my z. Z to the 4th, if I use my little index rule, that's going to be 2 with the remainder of 0. If I were to factor this out, that is 4 z's, and I would have a z and a z that would come out. So you can see that 2 z's will come out, no z's will stay in. When you simplify this, you just multiply everything that's inside by everything that is on the outside. So 4 times 2 times 3 is 24. I have a y to the first power. My index is even, and I pulled out something that is to an odd power. That is when you need to use absolute value. The only time you have to worry about absolute value is when your index is even. And then if you pull out something that has an exponent that is odd, that will need it. The z squared does not need the absolute value because z squared will always be positive anyway. So there's no need to tell me it will always be positive with absolute value signs. If you square it, it will be positive. It doesn't need it. All right. And then I am going to have just the 2, the x, and the y on the inside. And that is my answer here. So with addition and subtraction, you are basically looking for like terms. When you talk about variables like terms, that would be same variable, same exponent. When you're talking about radical like terms, the number on the inside has to be the same, and the index of your radical has to be the same. And so these all have an index of 2, so I know that's not the problem. But I have a 2, an 8, and a 3. None of those are the same. So in this process, I am going to first make sure that they are all simplified. The first one, the negative square root of 2, I cannot simplify that anymore. 2 is a prime. Minus, I have an 8. That can be simplified. I'm going to do the same process. A 2 can come out of that. A 2 will stay in. And then I have this minus square root of 3. 3 is prime. It cannot simplify. And now you can see that I have like terms. Remember, if you don't see a coefficient, it is a 1. So I have -1 minus 2. That is -3 square root of 2. And then I have this minus square root of 3. I can't do anything else with that. That is my answer. All right, so for this next one, you can see that we have all the same index, 3, 3, and 3. I can go ahead and combine these if I want, actually. the 3 cubed root of 5 and the negative 3 cubed root of 5 are actually going to zero out. So I can go ahead and zero those out. I'm not, however, done with this problem because I really do need to make sure that that 81 can't simplify. And so I am going to factor this into, and you can use 9 and 9 if you want to, that's fine. Or you can go ahead and just factor it with your primes. So this can be simplified. I already have a 2 on the outside. My index is 3. So now they don't have to group up in pairs of 2, they have to group up in 3s. So I have 1, 2, 3 there. So that means one of those 3s can come out. And then I have a 3 that does not have a group of 3. That one will stay in. And don't forget to put that index back there. And then I'm just simplifying what I can multiply. 2 times 3 is 6. Cubed root of 3. And I am done with that one. For multiplication, they do not have to be alike to multiply, but they either have to be both on the outside or both on the inside. You cannot multiply outside to inside, all right? So when I look at this, 5, that is on the inside of a root. 4 is on the outside of a root. 3 is on the outside of a root. 3 is on the inside of a root. So I can only multiply outside to outside, inside to inside. If it doesn't multiply, you just put them together. So like when I distribute this square root of 5 to that 4, I do not say square root of 20 because that is an inside to an outside. I just leave the outside number on the outside and the inside on the inside. That is 4 square root of 5. Okay? When I multiply here, it is a positive times a negative. This 3 is on the outside. It doesn't have anything to multiply to. Technically, there's a 1 on the outside of that 5. But the insides can multiply. I have 5 times 3. That's going to be the square root of 15. And then I'm going to do the same process that I did on my addition and subtraction. Can I simplify it? Well, no. 5 is prime, and 15 is 3 and 5. Nothing pairs up to come out. Are these like terms? No, they're not like terms. So at this point, I am done with this problem. This is my answer. If I could simplify like I did on the page before, I would, but nothing simplifies. All right, so for foiling, I'm going to do exactly the same thing. I'm just distributing twice and then combining any like terms that I have. I'm going to multiply this 1 through 1 times 2. That is just 2. 1 times 4 square root of 3. That is 4 square root of 3. I'm going to now distribute the square root of 3. Square root of 3 times 2. That 2 is on the outside. That 3 is on the inside. They stay the same because they cannot multiply. Square root of 3 times the square root of 3. That is the square root of 9. Anytime you multiply a root by itself, the root just goes away because the square root of 9 is 3 with no root. Okay, so the square root of 9 is just 3. So square root of 3 times the square root of 3 is just the number 3 without the root. And now I'm going to see if I have like terms. Well, now the 2 and the 3 are just constants. I can add them. So I have 2 plus 3 here. All right, so I am going to, oh, and I forgot my 4, by the way. Hang on, there's a 4. So these two can combine. I am going to do order of operations. So I have 2, and then when I multiply this 4 and 3, that's a 12. All right, so I have the 2 and the 12 that can combine. Then I have like terms here. 4 and 2 are my coefficients on the like index and radical of 3. So 4 plus 2 is 6, square root of 3. And then I'm going to say, can I simplify anything? Well, no, this is a prime. These are not like terms. So this is going to be my final answer here. So normally, just like we did on that foiling, square root of 3 times square root of 3, the square root goes away. But this is not a square root. This is a cubed root. So in order for that cubed root to go away, I need 3 of them. All right? If this were a bigger number, let's say this were 9, cubed root of 9, and I needed to get rid of it, then I would factor it first and see what I needed to multiply by. So if I had something like cubed root of 9 down here, well, I would say that's 3 times 3. So I would just need one more 3 to group it up, right, and get rid of it. In this case, I have a 5. I really can't simplify the 4 and the 5, so that's not going to work. So I am going to have to rationalize this one. I'm also going to look at my outside numbers to see if they will reduce. So before I do anything with my radicals, I'm going to look at my outside numbers, see if they can reduce like a normal fraction would. And I'm going to look at my inside numbers to see if they can reduce. So 4 and 2, do those reduce? Well, yes, they can reduce to 1 and 2. So I would now have a 2 on top with that cubed root of 4. And that cubed root of 5 would be all by itself. All right? Now I need to get the radical out of the denominator. Well, I have 1 5. I need 3 5s in order to do that. So I am going to multiply the top and bottom by those 2 more 5s. 1, 2, 3. That's how I get rid of a cubed root. I need 3 of them. Well, if I did that on bottom, I need to do that on the top. Whatever I did to the bottom to get rid of that radical, I need to do to the top. On the bottom, if I have 1, 2, 3 5s in a cubed root, the 5 can come out, which is my whole goal there. So I no longer have a root on the bottom. On the top here, I have my 2 on the outside, and I have 4 times 5 on the top. That is 100. Now I know that 100 can't simplify because 100, based on this, is going to be 4 times 5 times 5. Nothing groups 3 times. So that is as simple as that can get. I also cannot simplify the 5 and the 100. Why not? Well, the 5 is outside of a root. The 100 is inside of the root. Those cannot simplify. This is my answer here. So for this one, I'm going to do exactly the same thing. I am going to simplify first. All right? The reason I chose this one is because there is some reducing you can do on the inside. On the outside, I have basically a 1 up here and a 4. So the outsides cannot reduce. 5 and 4, those cannot reduce, but my variables can. M to the 4, M to the 4. Those straight up cancel. It's 1 over 1. So those are going to cancel to 1 over 1. N to the 4th over N to the 4th. Also cancel to 1 over 1. So already I have simplified this to the 5th root of 5, or not the 5th root of 5, the 3rd root of 5 over 4 cubed root of 4. All right, so here's the thing. I need to get rid of the radical in my denominator. What do I have? I have a 4. I can break that down to 2 and 2. I have 2 of those. It is a cubed root. What do I need to multiply by? So here's the thing. I already have 2 numbers in that root. So I can just do the cubic root of 2. Right. So I can just do the cubed root of 2 and the cubed root of 2. All right? That's why you break it down. So you can see how many of the number you have and then decide what do I need to multiply by. In the denominator, I have actually gotten rid of this root. I have 2, 2, and 2. in a cubed root. I can pull that 2 out of the root. So in the denominator, I still have that 4, but these 3 group up now, and they come out as a 2. In the numerator, I have a prime 5 and a prime 2. 5 times 2 is 10, and that cannot simplify. So I'm left with just simplifying my denominator here, which is the cubed root of 10 over 8. I cannot reduce these. 8 is on the outside, 10 is on the inside. This is my final answer here. I cannot reduce that anymore. So many of you set this up correctly or close to correctly, and then you didn't know what to do after that. So pay attention to this. Yes, I need to get this out of the root. A couple of things here. You cannot subtract these 2's, okay? This is not like terms. So some of you were reducing this first by simply subtracting these numbers. You cannot. This is 2. This is 2 squared of 5. It would be like x and y. You can't do it. They're not alike. Okay, so that's not how you get rid of it. You have to multiply by the conjugate, all right? The conjugate changes the second term only. It does not change the first term. If the first term is positive, it stays positive. If it's negative, it stays negative. All right? It only changes the second term. In this case, it was a minus in between. I will put a plus in between. And I will do that to the top and the bottom. All right? On the top here, I am simply going to FOIL. So I am going to distribute that 4. 4 times 2 is 8. 4 times 2 square root of 5. The outside multiplies to the outside. So 4 times 2 is 8. And I do not have anything to multiply with that inside, which is 5. So it stays. All right? On the bottom, anytime you multiply conjugates, you will end up with the first one squared, always minus the second one squared. That will always be what happens when you multiply conjugates. So my numerator has not changed. We're going to simplify that denominator. Everyone hopefully can do 2 squared. This second piece is where we saw some problems. I square the outside guy. 2 squared again, that is 4. That is being multiplied by squaring a square root. When I square that square root of 5, I get just a 5. All right? And then it's simply order of operations down there. 4 times 5 is 20. So on the bottom, I have 4 minus 20. All right? 8 plus 8 square root of 5 over 4 minus 20 is negative 16. All right? Here's the thing. You cannot simplify unless it comes out of everything. So I'm not just going to simplify one of these. I'm going to say what comes out of every single thing on the outside. So what can come out of 8, 8, and 16? 8. So we're going to divide everything by 8. 8 divided by 8 is 1. 8 divided by 8 is 1. 16 divided by 8 is 2. So you will get 1 plus 1 square root of 5 over negative 2. Or your answer key may distribute that negative to the top. I will take either one of these. In your answer key, it may show a negative 1 minus square root of 5 over positive 2. Those are the same answers. I will take either one. Okay, but your answer key usually distributes that negative to the top and takes it out of the bottom. So again, I only care about the denominator. I am going to do the conjugate of the denominator. The first one stays the same. I change the center sign, and I do that top and bottom. I multiply by the same thing. On the top, I am distributing. Negative 8 times positive 9 is negative 72. Negative 8 times positive 10i is negative 80i. 7i times 9 is 63i. And 7i times 10i is 70i squared. Okay? On the bottom, it is conjugates. The first one squared minus the second one squared. Always. When you multiply conjugates. I am going to simplify my numerator. Positive 70i squared. I squared equals -1. So when you have an I squared next to a number, it's just going to change the sign and the I will go away. This is the same thing as 70 times -1. That's what I squared is. So this plus 70i squared becomes minus 70. Okay? That's what happens there. So in the numerator, I can combine the negative 72 minus the 70. That's going to be negative 142. So I have negative 142 here. I have a negative 80i and a positive 63i. Those are like terms. So negative 80 and positive 63 is negative 17i. So that is my numerator right now. Let's look at the denominator piece. Denominator. 9 squared, that is 81. Minus, if I square this, the 10 squared is 100, and that is I squared. Same thing as above. The negative 100i squared becomes plus 100. 81 plus 100, my denominator is 181. If I could take something out of all of those, I would. I cannot. Or you're welcome to simplify it and say negative 142 over 181 minus 17 over 181i. You can split it up if that makes it easier for you to simplify. But I'll take either one of those in simplified form. But just like above, unless it can come out of all three like this, you can't simplify. If you split it, then you can reduce your fractions individually. They are both correct ways to do them. All right, so when you solve a radical, your goal is to try, if you can, to get the radical by itself. So on this first one, I need to move that 5 over before I do anything. I have 3x plus 31. 7 minus 5 is 2. I now have the radical by itself. This is an index of 2. So to get rid of an index of 2, I square both sides. When I square a radical with the same index, I just get what is inside. On the right-hand side, I just perform the operation. 2 squared is just 4. All right? Now I'm just doing a basic algebra problem. I'm going to subtract the 31 from both sides. 4 minus 31 is negative 27. And then I'm going to divide by that 3. X equals negative 9. You can go back up here and plug it in. The square root of 3 times negative 9 plus 31 plus 5 equals 7. This is negative 27 plus 31, so this is 4. Square root of 4 is 2. And that is the correct answer. (49), the radical is actually already by itself, so I can go straight to my squaring. However, this is going to be n squared. I will get what is inside here. Anytime you have a variable squared, you want to move everything to one side and factor and solve. So I'm going to move the n over and the 2 over. That becomes plus n minus 2 equals 0. Factors of 2 that subtract to give me 1. That's a positive 2 and a negative 1. If I set those equal to 0, this will produce negative 2. This will produce positive 1. I do, however, need to plug those back in. So in this case, when I plug them back in, Negative 2. Negative 2 equals square root of 2 minus negative 2. Negative 2 equals the square root of 4. That is not true. The only time you consider positive and negative root is if there's a variable involved. There is no variable when you check. So if you get the square root of 4, your answer should always be 2. Negative 2 is not the square root of 4 when you just have order of operations going on. So negative 2 does not work here. If I plug in a 1, I get 1 equals the square root of 2 minus 1. 1 equals the square root of 1. That is true. So my only answer here is n equals 1. Negative 2 is extraneous. 51, you can go straight to your squaring. On the left-hand side, you get just the x plus 3. On the right-hand side, you have a binomial. That means you are foiling that. So you're going to get x squared minus 6x plus 9 here. You have to foil it. Again, anytime you have an x squared, you want to get everything to one side. So I'm going to move the x over. I'm going to move the 3 over. So I have x squared minus 7x plus 6 equals 0. Factors of 6 that add up to 7 are just 6 and 1. When I set those equal to 0, I get x equals 6 and x equals 1. And once again, I need to plug those in. When I plug them in, square root of 6 plus 3 equals 6 minus 3. Square root of 9 equals 3. That is true. 6 is an answer. When I plug in 1, I get the square root of 1 plus 3 equals 1 minus 3. Square root of 4 equals negative 2. That is not true. 1 is not an answer. My only answer here is 6. Problem. In this case, you will never get both the radicals completely by themselves. So the best thing is to get one of them by itself. So I would move this group over by adding it over. And I would have the square root of 1 minus 3n equals 2 plus the square root of negative 1 minus n. And then I can square both sides. The left-hand side, 1 minus 3n. This is being foiled. So if I were to just write this foiling out, 2 plus the square root of negative 1 minus n, 2 plus the square root of negative 1 minus n. I am foiling that. So over here, 2 times 2, that is 4. 2 times the radical, that's just 2 times that radical. Again, 2 times the radical. Radical times a radical is just what's inside. So I can do a little bit here. I'm going to leave the left-hand side alone. On the right, I have 4 and negative 1. Those can combine to 3. And that minus n will not combine with anything. 2 radical, that is 4 times the radical. All right? Then my goal is to get that radical by itself. So I'm going to move this 3 over by subtraction. 1 minus 3 is negative 2. I'm going to move this n over by addition. Negative 3 plus 1 is negative 2n. And that will leave me the radical over here by itself. And now I would do the process that I did up here. Square both sides, get everything to one side, factor and solve. Remember, if I am squaring both sides, this left side is foiling. So you have 2 of those that you are foiling. On the right-hand side, you do have to square that 4, and then you're going to be left with what's inside there. So I have 4n squared plus 8n plus 4 equals negative 16 minus 16n. And anytime you have a square, get everything to one side. I'm going to move the 16 over here. 4 and 16 give me 20. The 16n over here. And then I have the 4n squared. I will say, when I have something like this, I'm going to divide that 4 out before I do my factoring, because 4 will come out of everything. So to make this a little simpler, I am going to divide this 4 out of every single piece before I factor this. So I have an n squared plus a 6n plus 5 equals 0, and now I have really easy factoring. N equals -5 and -1. And when you actually try both of those, they actually both work. Your answers are -5 and -1. So while it looks like a big problem, you just need to take it one step at a time. These are rational exponents. You need to get the base by itself. By that, I mean I need this n to be completely by itself. So in order to do that, I need to add the 8 over. On the left-hand side, I have -5n to the 2/3. On the right-hand side, I have -45. I still don't have the n by itself. I need to divide both sides by -5. I will get n to the 2/3 equals 9. Now I am ready to get rid of that exponent. For these, I need to raise both sides to the reciprocal. That is 2/3. So I need to raise it to the 3/2. That gets the n to the first power. 2/3 times 3/2 is n to the first power. So then I need to look at this. The easiest way to do this is to rewrite it as a radical. So I'm going to rewrite it as a root of 9. The bottom number, the denominator, tells me the index, which root I'm looking for. I'm looking for the square root here. The numerator tells me the exponent. So the square root of 9 cubed. Well, I can do that. The square root of 9 is just 3. So I have 3 cubed. 3 cubed is 27. One thing I need to consider here, this is the square root of a number involving a variable. When you have an even root with a variable, you also have to consider the negative root. So while the square root of 9 could be +3 here, when a variable is involved, you could have a -3 here as well. And so this could also be -3 cubed, which would be -27. So you have two answers here. Because you have a root of something and you still have a variable involved, you have to consider the positive and negative root for any of your even roots. So your final answer here would actually be +27 and -27.